Picture a toy car moving down a straight road. It has a starting line and a destination. If we measure the whole trip, we might find that the car traveled a total distance of 100 kilometers, and the journey took exactly 2 hours. Standard arithmetic handles this effortlessly. You divide 100 by 2, and you get an average speed of 50 kilometers per hour. But that 50 kilometers per hour is a historical summary. It tells us the overall pace of the completed trip, but it reveals absolutely nothing about what the car was doing at any specific moment along the way. Try asking a much harder question. How fast was that car moving at exactly 1 hour, 17 minutes, and 32 seconds? At that exact frozen second, the actual speed could wildly deviate from the average. The car might have been accelerating at 70 kilometers per hour or stopped completely at 0. This formula shows our mathematical breakdown. Speed equals distance divided by time. It requires measurable duration, but a frozen instant has a duration of exactly 0. If no time passes, the car travels 0 distance. Dividing 0 by 0 crashes our foundational rules. Standard algebra cannot solve this paradox. To measure the physical reality of right now, we need a mathematical engine designed specifically to handle the infinitely small. Instead of freezing time completely and breaking the equation, we can use a conceptual workaround. We examine a smaller slice of the trip. This timeline represents our measurement window. We start by calculating the average speed over 1 full second. Then we shrink that window to 1/10 of a second, then down to a single millisecond. As that time interval becomes increasingly microscopic, the car's speed has virtually no room to fluctuate. The average calculation stabilizes, honing in on one undeniable target number. In mathematics, this specific destination is called a limit. A limit is a precise mathematical guarantee. It bypasses the trap of dividing 0 by 0 by analyzing the exact value that a moving number is trying to become. This graph illustrates the first rule of limits, getting close. We add a block of 1, then a half, then a quarter. The total continuously creeps toward a destination of 2. Every new piece added is smaller than the last, meaning the total never overshoots the target. In calculus, approaching a destination does not require you to actually arrive or touch it. Here we see a target surrounded by shrinking rings. This represents the second rule, the epsilon challenge. We demand the value get within an error margin of 1, then 1/10, then 1,000th. A true limit must be able to pass every single epsilon challenge, no matter how microscopically thin you make that allowed distance. But imagine a train speeding toward a station. It rolls within a millimeter of the platform, getting incredibly close, but then continues right past it. The train got close, but it didn't remain close. Because it pulled away, the station fails the definition of a limit. This completes the architecture of a limit. It requires a value to get as close as you demand and permanently stay there. This diagram shows how these abstract rules apply to physical geometry. We place a square inside a perfect circle. The straight edges leave wide, empty gaps along the curve. Now we multiply the sides. An octagon fills more of the space. A shape with 100 sides and then 1,000,000 sides causes those jagged gaps to vanish as the polygon expands. As the number of sides approaches infinity, the polygon gets permanently trapped. Its area falls within the microscopic epsilon margin of the true circle's area. By utilizing an infinite progression of straight, calculable lines, we can precisely map a continuous, perfect curve. We can now take this exact tool back to our toy car to finally solve the paradox of right now. Look at this graph plotting position over time. If we pick 2 distinct points and draw a straight line between them, its slope gives the average speed. Now we execute the infinite zoom. We shrink the time interval, sliding the second dot closer to the first. As the time gap reaches a limit of 0, the 2 dots merge. The connecting line flattens into a perfect tangent, resting on a single point. The slope of this tangent line represents the instantaneous velocity. We have calculated the exact speed of the car at a frozen timestamp. By using limits to define infinite closeness, we bridge the gap between an average of the past and the reality of the present. This calculation, the derivative, turns the study of static snapshots into the study of continuous change.